Okay, let me go through some of these solutions for the practice exam. First one, we had a rational function here. You'll notice that on the top I factored it out, the bottom I factored it out. Hopefully that bottom will be a pretty quick process for you now when you see something in the form a squared minus b squared. The top had a cubed plus b cubed. It should be something that you should be loosely aware of, even if you have to kind of do some trial and error before you actually get cubed. You either have a cubed plus b cubed or a cubed minus b cubed. So once I get that factored out, I notice I have an x plus 4. I cross them both out. When I put this fraction or this function in lowest terms, as you'll see right here, it's actually a new function. If I graphed this thing and then graphed the original, they would look the same, except this one's going to have a hole in it. So this is that concept of holes that you saw popping up throughout the chapter 4. So I know that I have a hole at x equals -4, and then let me go and jump down to part C right there. The question is, what's the y coordinate of that hole? And if you put -4 back into the original function, you're going to find that you'll get something undefined, often 0 over 0 or something like that. So the way that I get the y value is by putting the -4 in this new function that I created by canceling out the x plus 4, because this new function is a complete continuous function and it won't have any holes in it. So that'll get me that y value here of -6. The domain here, I'm going to look at both the hole and the y asymptote, because in both cases the function is not going to exist. And vertical asymptote is coming from that x minus 4. Let's see, no horizontal asymptotes. Of course, there's those 3 rules where you're looking at the power of the highest power of x in the numerator, highest power of x in the denominator. And then if they're the same, you just divide the coefficients, and that's your horizontal asymptote. If the one on top is higher, like in our case, we don't have any, and if the one on top is lower, it would just be a horizontal asymptote at 0. I plug in to get the intercepts. Notice that I don't have any x-intercepts. I have this b squared minus 4ac less than 0. What does that mean? Well, keep in mind on the quadratic formula, this is what you would find underneath the square root. So if that's a negative number, I'm not going to have any roots. If that's equal to 0, I'll have one root, a double root at 0, and or a double root, I should say. And if it's greater than 0, I would have 2 roots, 2 real roots. Okay, and I look at the end behavior and graph that. Solving this rational inequality, there's a couple different ways to do it. I like to set it as an equals because then I'm going to get the same critical points. So going through there, I get x equals 4 and -3, which I plot here with open circles. Now I could plug those -3 and 4 into the original just to make sure that, to find out if I need to close those or not. In this case, I don't. And when you're going through, if this is greater than, or if it's a less than, those are going to be open dots. Greater than or equal to, less than or equal to, they'll be closed dots. But you'll notice I have a third critical point here. Where does that come from? That comes from the domain of the original function. I notice that x cannot be -1. Then I put a test point in from each of my 4 regions. I find out that these 2 regions are okay, and so that's my domain. Number 3, these we can do it in several different ways. I'm just choosing some function for f, and it has to be non-identity. In other words, I can't have f of x equals 1. Otherwise, you could just have that for all of these without really understanding the concept. So notice, though, I have 3 different options in this case, and probably more, but 3 that I've written down for my f of x. And let's just take the middle one. If I let f of x be x squared, then my g of x, I know that whatever this x squared is, or whatever this f of x is, it's going to get plugged in for my g, of x, and then I need to duplicate this function ultimately. So when I plug that x squared into x in g of x, I'll have 4x squared minus 3, which is what I should have. And notice that would be the same in any of these cases. Okay, number 4, a couple of things I just want to point out. First of all, why do they have this x greater than or equal to negative b over 2a? Because we just want one side of a parabola, and in this case, the right side. Why? Because we can't have a one-to-one function, and we can't have an inverse if we would have an entire parabola. So if a function, in order to be a function, it has to pass the vertical line test. But in order to have an inverse, it has to pass the horizontal line test. No horizontal line should go through and hit more than one point on the function. And that's why we just take the right side of the parabola. And that's also why down here we only took the positive, or I guess right here we only took the positive when we took the square root. Typically that would be a plus or minus out front. And one thing I wanted to point out, I noticed a lot of mistakes in the first exam. If I see the square root like this, that means that this number is a positive number. If I take the square root of both sides, like in this step, then typically I would need to do the plus or minus. So the only reason I'm not doing it here is because I was explicitly told to take the right half of the parabola. But in general, when I take a square root of both sides, I do need to put that plus or minus there. The only thing is, what is the square root itself is actually a positive number, or 0, but then we may have a plus version of it, or we may have a negative version of it. And by the way, you'll notice that the inverse function of that, which is that general parabola, is basically the quadratic formula with this addition of 4ax in there. Okay, number 5, notice that I set it up just like I would set up a quadratic, and then I factor it out. Instead of having an x in both cases, I just have x to the 2/3. Remember that when we multiply something of the same base, so x to the 2/3 times x to the 2/3, we're going to just add the powers, and that would give us x to the 4/3. Other than that, we're just, again, setting up the inequality, looking for critical points, and then testing a point from each section. Okay, here, when I'm thinking of domain, 3 things I'm looking for. I don't want a I don't want a 0 or a negative inside of a log, so it has to be greater than 0. I don't want a negative number under a even root, so this has to be greater than or equal to 0, and then I don't want to divide by 0, which is not a case in this problem. So again, I set that inequality equal to 0. I know that it has to be greater than 0, so I set it equal to 0 so that I can find the critical point there. And then I also notice that my x has to be greater than 5, but in this case, all of my x's that would be allowed by the log would be greater than or equal to 5. Now that 5 is shaded in not because it's part of the domain, but because I did this x is greater than or equal to 5 first, and then once I realized that no, I do have to be higher than 6, so I really shouldn't have colored that in, and notice when I write the final domain, 5 is not part of that. Sorry, on the number 7 here, this is this concept of viewing logs flexibly so that we can solve them analytically. So 1/2 would be the same as ln e to the 1/2 because you can look at it as by the power of logs we could put that 1/2 out front, and then natural log of e is just 1, so we'd have a 1/2. Why would we do that? Well, because if we have both of these in terms of a natural log, then we can combine them because they're being subtracted, so they would end up getting divided inside of a single log. Okay, solving this for x, we're just going to take the log. Now you could take the log base 10. You could take log base 3 for all you wanted, log base anything in this problem. It really doesn't matter, because as soon as we have the logs there, we can use the properties of logs, such as putting the exponent out front, which we did in both of these cases. Here I just took the xlnc over, factored out an x, and then divided. Keep in mind that log of some constant is just like a number that you're used to working with. Okay, number 9, setting it equal. Here's an important step right here. So when I have a variable up in a power, how do I get that out? That's where I use logs, because I know if I take the natural log of both sides, then I can pull that power out front, and then the natural log of e would be 1. Notice here I could have used any log. I didn't have to use the natural log, but the problem is if I used a log, I could still get that t out, but if I have log base 10 of e, then I couldn't, it would still be hanging around right here. I couldn't get rid of it like I did here. I chose the natural log so that when I took the natural log of e, that would be 1. And note, I'm not going through the entire working out of all these problems, but you can always feel free to write me with any of these problems if you don't understand the work that I did. Okay, number 10, solving this analytically. I know that this 4 can get pulled out front. Why can't I pull this 2 out front? Well, because the rule is if I have natural log of something that is squared, and the entire thing has to be squared, by the way. For example, if this was 3x to the 4th, I could not have pulled that 4 out front. I can only pull it out because what was inside the log, the x, the entire thing was getting raised to a power, so I can put that power out front. In this case, though, the x is not what's getting raised to the power, it's the entire log of x, which means, as anything that gets squared, I'm just taking this times itself. So I wrote it 2 times here. And then I simplified by dividing by ln of x. So in other words, I have 4 equals ln x, and then that gave me one of my solutions. But anytime I divide by something that could be 0, I have to include that as a possible solution. So that's why I write either ln x equals 0, in which case we can solve and find that x equals 1, or, and then I show what would happen if I cancel out and divide by ln x on both sides. So that gives me my 2 critical points of x equals 1 and x equals e to the 4th, and then I just test the regions there. Now, why do I have this critical point of 0? Well, that comes from the original, because x has to be greater than 0, right? If I have x less than 0, I couldn't take a log of it. So that's where I get my 3rd critical point there. And finally, 3 functions. One thing to keep in mind when we're looking at domain is the domain has to work for the inside function and for the overall function. Now, we don't care so much about the domain of f of x. If we found an x that was in the domain of g of x and was in the domain of f of g of x, we would say it's in the domain of the overall composed function, even if it's not in the domain of f of x. But even if it's in the domain of f of g of x, but it's not in the domain of g of x, then it would not be in the domain, if it's not in the domain of the function that we get after we simplify f of g of x, then we can't include it in the domain if it's not in the domain of g of x. So that was confusing. We start with the innermost function, then we go out. If there'd be a 3rd one here, then we have to check the domain of g of x, f of g of x, and say h of f of g of x. But we don't worry about f of x in that case, or h of f of x, or h of x. So we're only starting on the inner function and going out one by one, and it does have to be in the domain of all of those in order to be in the overall domain here. Okay, that's it, and again, please let me know if you have any questions. Just shoot me an email, and good luck as you study. Bye.